Hello everyone. Today we are going to deal with another application of quantum mechanics, which is barrier transmission, or we can just say that it has a leakage of a particle through a thick rectangular potential barrier, or sometimes even it is called as quantum mechanical tunneling. So let's see in detail with a mathematical background for barrier transmission. For that, first, let us see the potential along y-axis, and we are taking a thick rectangular barrier which is extending from 0 to L. Along x-axis we have the position. So from x equal to 0 up till x equal to L we have the barrier which is rectangular in shape, and along y-axis we have the potential which is V of x. And this can be divided into three regions for easier understanding, and we are going to see what is the wave function in each of the region. Then let us consider in region 1 we have the wave function as xi1. In region 2 the particle can be described by the wave function xi2, and in region 3 we are using xi3 as the wave function. Then if you consider a stream of a particle, let us say it is having a mass m and it is approaching the rectangular barrier from the left. So it is considered as an incident wave. Classically, if the energy of the particles which is incident, it is greater than the potential barrier, that is V of x, then easily the incident wave or the particle can pass through it, because energy is greater when compared to the energy of or potential of the barrier. But if energy is less than the potential of the rectangular barrier, then it will be always reflected back. And classically it is always reflected back, but quantum mechanically we say that there is a certain probability of a particle to penetrate the barrier and get transmitted. So even if the energy is less than the potential of the barrier, then also the particle can be transmitted. So it is a transmitted wave which will be in region 3. So this leakage or tunneling and the corresponding wave functions and final conclusions we are going to study in detail. For that, we need to know about its potential. So the potential function allows us to understand the exact solution of equation of motion. And for this system, which is a rectangular barrier, we have V of x, that is the potential, is equals to 0 for x less than 0 or greater than L. That is, outside the barrier potential is 0, whereas from 0 up till L we have the potential V of x is equals to V naught. Let us call it as equation number 1. In order to understand about the nature of the particle and its movement for energy less than V naught, we are going to consider the equation of motion in quantum mechanics, and it is the time independent Schrodinger equation, which is d square xi by dx square plus 2m by h cross square into E minus V of x into xi equal to 0. Let it be equation number 2. Then for energy of the particle or system of particles less than the potential barrier, that is V naught, we find certain tunneling. So let us find out different wave functions for each region. So case 1 we are considering in region 1, where we have the incident wave as well as reflected wave. So in region 1 we have considered the wave function to be xi1, and here the potential V of x is equal to 0. And if you substitute the value in equation number 2, which is the Schrodinger equation, V of x is equal to 0. That's why we have d square xi1 of x by dx square plus k square xi1 of x equal to 0, because wave function is xi1, V of x is 0, and we know that 2me by h cross square is nothing but k square. Let us call it as equation number 3. Coming to the second region, that is case 2, where we have considered the wave function xi is equals to xi2, and the potential V of x is equal to V naught. So when you substitute it in the Schrodinger equation, we get d square xi2 of x by dx square minus beta square xi2 of x is equals to 0, where beta square is equal to 2m by h cross square into V naught minus E. So we have just shifted it so that we can represent this wave equation in terms of beta square. Then coming to region number 3, where we have the transmitted wave. Here the wave function is xi3 and potential V of x is equals to 0, where x is greater than L, that is in the region number 3. Again substituting the value of V of x equal to 0 in Schrodinger wave equation, we get equation number 5, where again we have defined 2me by h cross square as k square itself. And we can observe that the first region and the third region, they are having the similar wave equation, but the difference is with the wave function xi1 and xi3. So these are the second order differential equations, and we know that the solution is in terms of the exponential functions, because it is something like a simple harmonic motion equation. And solution for equation number 3 is xi1 of x is equals to a into exponential of ikx plus b into exponential of minus ikx. Let us call it as equation number 3a, which is the solution for equation number 3. Then the solution for 4 will be xi2 is equals to c into exponential of beta x plus d into exponential of minus beta x. Here there is no imaginary or I term, because we have defined a certain amount of potential here. Let us call it as 4a. And finally, the solution for equation 5 is xi3 is equals to g into exponential of ikx. So what is the difference between the three equation or solution is that xi1 is the wave function related to the region number 1, where we are having two different terms. One is a into exponential of ikx, and this is the function for the incident wave, which is in region number 1, and b into exponential of minus ikx represents the wave function for the reflected wave. Coming to 4a, xi2 is the region within the potential barrier, and again here also the particle can move from left to right, or even it may move from right to left. So here c into e raised to beta x will be along positive x-axis, whereas d into exponential of minus beta x will be in negative x-axis. Coming to the last solution 5a, xi3, it is with respect to region number 3. Here we are having only transmitted wave. That's why we are defining only one term, which is g into exponential of ikx. So this is the difference between the three. So based on this, first we need to find out what are the coefficients or what are the value of a, b, c, d and g. Or else we can just define each term in terms of another term. So we are going to do one thing here. We will find out the value of A, B, C as well as D in terms of G, so that it becomes more simpler to explain the transmission as well as reflection coefficient. To find out these coefficient A, B, C, D, we need to consider the boundary conditions, because if you don't consider the boundary condition, then you can't find out the solution for this. So boundary condition, we know that the conditions are that the wave function should be continuous at x equal to 0 and x equal to L, which is the boundary of the rectangular barrier. Because you can't just say that incident wave is incident on the barrier and from other point it will penetrate inside the barrier. No, because if that is so, then the wave function is not continuous, as well as at one value of x we are having two different values of xi, which is again violating the main criteria for a function to be a wave function. It should be single value. That's why we are going to consider these two conditions, that is xi should be continuous at the boundaries as well as the derivative of xi should be continuous at x equal to 0 and x equal to L. So in the solutions we are going to find out the values of A, B, C, D by using this boundary condition. First, let us consider the interface of region 1 and region 2. That is nothing but at x equal to 0. That is the first boundary where the barrier just starts. So at the interface we have xi1 equal to xi2. The wave function is single valued, and at x equal to 0 both the wave functions which is defined in region 1 and region 2 should be equal. And according to the first boundary condition, xi1 at x equal to 0 should be equal to xi2 at x equal to 0. Then only we say that the wave function is continuous. And we already found out what is xi1 and xi2 from equation 3a and equation 4a. So just substituting and putting x equal to 0. So exponential of 0 will be equal to 1. And finally we have the relation a plus b equal to c plus d. Let us call it as equation number 6. Then coming to the second boundary condition, which is derivative of xi1 of x at x equal to 0 should be equal to derivative of xi2 of x at x equal to 0, because the derivative also has to be continuous, which is the second boundary condition. So we need to differentiate xi1 and xi2, and a is constant, exponential of x is again e raised to ikx itself, again multiplied by I into k, which is the coefficient of x, plus b into exponential of minus ikx into minus ik is equals to c into e raised to beta x into beta plus d into e raised to minus beta x into minus beta. So I have taken the derivative of xi1 as well as xi2. Next, putting the value of x equal to 0 in the equation, exponential terms will be equal to 1. That's why we are remaining with ik into a minus b is equals to beta into c minus d. And if you simplify, we get another equation which is again with respect to a, b, c and d. Let us call it as equation number 7. So equation number 6 is a plus b, equation number 7 is a minus b. So we are having two simultaneous equation which can be solved to find out a as well as b in terms of c and d. So when you add equation number 6 and equation number 7, we get 2a is equals to beta by ik into c plus d minus beta by ik into d. We have just added both the equation. So when you club the terms with respect to c and d and divide by 2, we get the value of a in terms of c and d, which is equal to 1 by 2 into c into 1 plus beta by ik plus d into 1 minus beta by ik. Let us call it as equation number 8. Similarly, you can find out b value by subtracting 6 and equation number 7, and b will be just varying with respect to signs, that is half into c into 1 minus beta by ik plus d into 1 plus beta by ik. Let us call it as equation number 9. But here again the amplitudes or coefficients, which are a, b, c and d, we are representing one amplitude with respect to another two amplitude. A is defined again with respect to c and d. B is also defined again with respect to c and d. So if you find out what are the values of c and d, easily you can simplify this equation. For that, let us consider the interface of region 2 and region 3. That is the position where x will be equal to L. That is the another boundary. So whenever we are applying the boundary condition, we need to consider boundary itself. Anywhere or everywhere we can't apply the boundary condition. So here the boundaries of the barriers are at x equal to 0 and at x equal to L. So now considering x equal to L position, that is the interface. Now boundary condition 1, which states that the wave function should be continuous at the boundary. So xi2 of x at x equal to L should be equal to xi3 of x at x equal to L, because region 2 is expressed in terms of xi2, whereas region 3 is expressed in terms of xi3. So when you put the values from the solution, we get equation number 10, where c plus d term will give you the g term. Then according to boundary condition number 2, we have the derivative of xi2 at x equal to L is equals to derivative of xi3 at x equal to L, which states the continuity. When you take the derivative and equate it, we get equation number 11, which is c into exponential of beta L minus d into exponential of minus beta L is equals to ik by beta into g into exponential of ikl. Now again we are having two simultaneous equation. So now again adding and subtracting both the equation, we can find out the values of c and d. So when you add it, we get the value of c as g by 2 into 1 plus ik by beta into exponential of ik minus beta into L, which is equation number 12. And when you subtract, that is equation number 10 minus equation number 11, we get the value of d. So we need to just do two steps, simplify, rearrange. Then d will be equal to g by 2 into 1 minus ik by beta into exponential of ik plus beta into L. So this is equation number 3. So now what we have done? The coefficients or the amplitudes of each term, that is A, B, C and D, we have found out. But A and B is with respect to C and D, that is two different terms. But C and D is with respect to G, which is the amplitude of transmitted wave. So if you put the value of C and D, that is from equation number 12 and equation number 3, in our previous equation which defines A and B, we can find out the value of A and B in terms of G. So doing that, substituting the value of C and D in equation number 8, we get A value where we need to rearrange some terms. So G by 4, 1 by 2 is there. So G by 2 is taken outside. So G by 4 into exponential of IKL is common. When you take it common, we have within the bracket exponential of minus beta L term clubbed with 1 plus Ik by beta into 1 plus beta by Ik. So we need to just multiply. 1 into 1 is 1. 1 into beta by Ik is beta by Ik plus Ik by beta plus Ik by beta into beta by Ik will be equal to 1. In the same way, the latter term. Again simplifying. So here we are clubbing the term of exponential of beta L and exponential of minus beta L. After that, in order to use the equation, which is a formula, we are just clubbing, that is G by 4, 1, 2 is taken within the bracket. So G by 2 exponential of IKL remains as it is into 2 times of e by beta exponential of beta L plus e raised to minus beta L by 2, which is something like e raised to x plus e raised to minus x by 2, which is equal to cos hyperbolic of beta L, that is cos hyperbolic of x. That's why we are doing this simplification. And coming to the second part, that is we are collecting the term of beta by Ik as well as Ik by beta. So exponential of beta L minus exponential of minus beta L by 2 is equals to sine hyperbolic of beta L. So again simplifying, that is taking 1 by 2 within the bracket, we get A is equals to G into exponential of IKL into cos hyperbolic of beta L plus I by 2 into beta by k minus k by beta into sine hyperbolic of beta L, which is equation number 14. So now what we have done? We have found out the value of A in terms of G. So the incident wave amplitude is in terms of transmitted wave amplitude. So if you just subtract or do some functions, you can find out how much particles are within the barrier or what amount is involved in the tunneling as well as reflection. So when you do the same, that is when you substitute the value of C and D in equation number 9, which is the term B, we get the value of B is equals to minus I by 2 into G into e raised to IKL into beta by k plus k by beta into sine hyperbolic of beta L. So here the inside term, that is bracketed term, is having different sign when compared to 14. So all are now, that is A, B, C as well as D are expressed in terms of G, which is the amplitude of the transmitted wave. So all the waves are in terms of transmitted wave. So by using these equation of A, B, C, D as well as G, because all are in the same parameter, that is with respect to G, easily we can simplify to find out different conclusion. And in our coming class, we are going to study about two important terms, which is transmission coefficient as well as reflection coefficient, and find out some of the conclusions out of it. So this is actually for the particle if energy is less than V0. Classically, when energy is less than V0, which is the potential of the barrier, then particle cannot penetrate into the barrier. But quantum mechanically we say that even if the energy of the particle is less than the potential of the barrier, there is certain probability or chances of the particle penetrating or passing through the barrier, which is termed as barrier transmission or tunneling. So based on all this concept, we are going to find out the transmission coefficient as well as reflection coefficient in our next class. So go through it. This is for today's class. Thank you.